So good evening students. So today's topic we are continuing electromagnetic theory, that to Gauss law, okay, or Gauss theorem. So electromagnetic theory, last class we discussed about Coulomb's law, where I discussed about force of attraction between the charges, right? So in Coulomb's law we discussed about force of attraction of the charges, and also we did some problems, right? Now today's class we will discuss more briefly about the Gauss law, why Gauss law is needed. Okay, for that we have to go some more the topics other than force. We need to know about field. Okay, so what is field? Then we can discuss about potential. So these are the topics today we need to discuss. Now, first of all, before we need to go to Gauss law, I just want to know what is electric field. Okay, so we know electric force, it is the force of attraction between the charges, where two charges always feel the force of attraction or repulsion. Now, what is field means? It's a region or space. If you take any charge, okay, the charge will have its influence on the space. The charge will have its influence on the space. That is what we call electric field. Electric field. So very, very important, electric field. Yeah. What is electric field? If you take a charge, okay, this charge has a field around it. It may be any dimension, like how much area it occupies, the field we need to find. So this charge, whatever I place here, this charge will have its influence around this area. Okay, what it means, see, this charge will hold this area. Because of this charge, there produces a field around it. This field is what we call electric field. It's a region or space surrounding a charge. Okay, it's a region or space surrounding a charge. That's why the name field is there. Okay, so what that space is actually, you see, whenever we keep a charge, okay, from the charge there will be some force it will develop. How you can experience that? If there is two charges, for example, one more charge is there, okay, Q2, this is Q1 and this is Q2, then you can see that there is a force of attraction or repulsion based on the polarity of charges will be there. But instead of two charges, if there is only one charge is there, instead of two charges, if there is only one charge exist, then what is the force really does? Will the force will be there? Is force exist still also? Still force will be there? That is the question. When there are two charges, definitely force will be there. But if I take out one charge, will the force exist? Will the force exist? That is the question. So that concept we can explain only by using this concept of field. If I remove one charge and I will keep only one charge, out of two charges, one charge I will remove, so that only one charge will be there, still the force exists, means yes, that force is what we call field. This force only what we call field. This is what we call electric field. Okay, it's a region or space where the charge will has its influence. Okay, so that is what we call field. And one more thing is very clearly we need to mention here is, what is that is, if for example, if I want to check how much region this charge has its influence, you need to take one test charge. Take one test charge. This is a source charge. This is a source and this is test charge. You see, if I bring a test charge of, for example, 1 coulomb, or very small or very light values, 1 nanocoulomb, okay, 1 microcoulomb, anything, This is very, very least. Okay. The test charge I will bring near the source charge. So what is the meaning of test charge? Means this is the charge which you need to test, which is used to test the field of the source charge. Okay. Now you see what I will do is this test charge, okay, small, this is q1 and this is small q, or I can take this source charge as capital Q. Capital Q I will take. Okay, this is maximum charge, maximum amount of magnitude will be there. It's a huge charge, and this is a source charge, so its magnitude is more. Magnitude is more. And the test charge is having less magnitude. Less magnitude. Whenever we bring the test charge near the source charge, okay, so what it will do, that is the concept. So here you will understand the field. If I keep the test charge here, if it doesn't, the test charge not experiences anything. That means this source charge is not applying force on it. Correct, right? Now, if the test charge brings very, very near, since it is not experiencing anything, okay, so that means this region is, it is not actually influenced by this source charge, okay. But when you bring the test charge very, very, very near, very, very, very near, for example, if it enters this region, okay, at one point P, now this source charge will attract this test charge, or it will repel the test charge. But actually it will repel, because test charge I will always take positive charge, okay, positive charge. This test charge is always positive charge. It's a unit, and the test charge is also a quantity, its magnitude is unity. I will not take huge amount. Okay, so whenever I brought this test charge near this source charge, definitely there will be a force of repulsion, because this is also positive charge and the test charge is also positive charge. When I brought near this point P, what happens? When I brought this near this point P, definitely this test charge will experience a force of repulsion. It's common, right? Because both are positive, the source charge will be there, this test charge will be there. When till point P, it never feels anything. The test charge never experience any force. But once it enters this region, okay, the region is what we call electric field. Once the test charge enters this electric field region, okay, then it will experience a force of repulsion. That is what we call electric field, because this region is completely under the influence of source charge. Okay, now one more question. Sir, we know according to Newton's third law, what Newton's third law says, for every action there is an equal and opposite reaction. Action has a reaction, right? Action will have a reaction. So this source charge will experience, will apply force on the test charge. Definitely the test charge also apply force on the source charge. Okay, so there may be a chances that there is a disturbance in the position of the source charge. Correct, right? When I brought this test charge near the electric field, it will experience a force. Even this charge, source charge also will experience a force. There may be a chance. Okay, so that's why we will bring a test charge which is very, very small. Okay, that's why we will take a unity. It's very, very small number, so that the source charge does not disturb. The source charge, this portion, this position of the source charge does not disturb. Sorry. If it disturbs, what happens? If it disturbs means, what is the method of, what is the use of bringing test charge? We are bringing test charge to test the field, correct, right? So that's why the source charge is always a huge magnitude and the test charge is a very less magnitude, and that too its value is unity. It's always 1. Okay, it's maybe 1 macrocoulomb, 1 nanocoulomb. It's very small. So that's why that is the concept. It's the region or space. So electric field you can define as, it's the region or space surrounding a source charge. You can write, okay, it's a region or space. it's a region or space surrounding the source charge, surrounding the source charge where the test charge experiences a force of repulsion, where the test charge experiences a force of repulsion. So this is what we call electric field. This is the region, space surrounding the source charge. So source charge is always having maximum magnitude and the test charge is always having a minimum magnitude, and this source charge will be have its region or space, okay, where that region or space where the source charge has its influence is called electric field. Okay, that is a field. Field means area. So it has an electric field. In the sense that field is filled with electric field lines actually. And the test charge we will bring near the source charge, where the test charge will experience as a force at one particular point. Till that point, the charge will have its field. Okay, if for example I take this point, it's not feeling anything, it's not experiencing any force. So that is what we call electric field. Okay, and the electric field is always represented by the letter E. Electric field is represented by the letter E vector. Okay, so it is always, we can write force per unit charge. It is force per unit charge. Yeah, please take this. So I will discuss more about the electric field. Okay, why it's force per unit charge. Okay, so yeah, please take. Yeah, so now you see, as we discussed, if there is a source charge, okay, this is a source charge. Now surrounding the source charge there will be field, so we will call it as electric field. Okay, so where the test charge, a small charge, if it enters at that field, it will experience a force of repulsion. Understood? Now this force of repulsion, why it will experiences? Okay, because this test charge is a positive unit number, okay, and the source charge is a maximum magnitude that we discussed. But for example, if the source charge is negative, correct, right? Now what about test charge? If the test charge is, I am taking test charge always positive, okay, test charge always positive, I will take positive unit number. If it is negative, at one particular point, if I bring the source charge, test charge, this point P, now what happens? Immediately the test charge will attract towards the source charge, because it is negative, that is positive, because I am taking the source charge always positive. I am taking the source test charge always positive. Source charge may be positive or negative, but test charge is always positive. So what happens? It will start attracting. At that point, from that point, there exists a field that you can experience. Okay, so you can say that always I am taking the test charge. The property of the test charge is it is always a positive unit charge. It is always a positive unit charge, always a positive unit charge, unit small fragmented charge, very small charge it is, okay, very less. Okay, now so electric field is represented by E. Okay, what it means? What is electric field? It's Whenever you bring the source charge and test charge very near, there exists a force of attraction between source charge and test charge, right? You know Coulomb's force, it is 1 by 4 pi epsilon naught, okay, Q1 Q2 divided by R square. Understood? Now you see 1 by 4 pi epsilon naught. What is Q1? Source charge Q. What is Q2? Test charge, which is 1 positive charge. Okay, and the distance between them is R square. So this is the force between the source charge and test charge, and you can write it's a vector. Now you see, this force is same as electric field E. E is equals to 1 by 4 pi epsilon naught Q divided by R square into R cap. Even electric field is a vector. Understood? Now you see. So force and fields are similar when you bring a test charge near the source charge. Understood? Now here you see, the force formula is Q1 Q2 by R square, okay, but the field is just Q by R square. So what is the relation between Coulomb force and electric field is, so electric field E is equals to force divided by one charge Q, okay, and the charge is very fragmental charge, very small quantity, okay. So that's what F is equals to, E is equals to F by Q, or you can also say F is equals to QE. F is equals to QE. Force is equals to charge into electric field. Very important relation. Maybe you heard so many times, right? Yeah. Just yes. That yeah, QE. So F is equals to QE. So this is what the force. And what is the unit of electric field? So E is equals to FIQ. So E unit is, F force is Newton by charge is Coulomb, so it is Newton per Coulomb. That is the unit of electric field. Okay? So please take. Yeah, next. Yeah. Now here you see. So in the last slide we saw that whenever if you have a positive charge, source charge, what happens? This positive charge is repelling. So scientists thought, what is this field actually? How we can represent field? So field is represented with some geometrical lines. Okay, so they started, giving some representation of the field. How we can represent a field? What is actually there in the field? So in field there are electric field lines. Electric field lines. So this is what geometrical representation of electric field, and it's an imaginary pictorial representation. Okay, so pictorial representation of electric field is electric field lines. Electric field lines. See. Okay, and this is positive charge, and this test charge also whatever bring is positive. So here also what happens? The force of repulsion will be there. Force of repulsion means the source charge always push the test charge away from it. That's why the electric field lines are move away from the charge. Okay, so electric field lines you can discuss here. Electric field lines you write here. I'll write in the next. Yeah, whenever you take a positive test charge, positive source charge, where it is positive, okay, where the electric field lines are always move away from the charge. Why electric field lines that we introduce? To represent the electric field. It's a pictorial way of representation of electric fields. These lines are so dense. Okay, you see here? Yes, this is the way of representation of electric field. Understood? Huh? Okay, so these electric field lines are always originate from the positive charge. Okay, originate from positive charge. See, from positive charge. That's why if you place a test charge here, what happens? These field lines are acting on the test charge and it is moving away. Okay, that's why these field lines are originate. That's why electric field is always outward from the positive charge, positive source charge. Okay, now if I take a negative charge, for example, minus q, okay, now if I take one test charge of plus, I always say test charge will always take, you know, positive charge. Now what happens? This test charge will be attracted by the negative charge, right? So what is the direction of electric field? This is direction. That's why the direction is towards the electric charge. The electric field lines are always towards the negative charge. You can write like this. So it is attracting, right? It is attracting the test charge. So it is, you can always write terminate. Electric field lines terminate at the negative charge. At the negative charge. They originate at positive charge and they terminate at negative charge. So this is another example of electric field lines. So electric field lines are like, they are the representation of electric field. Okay, so how electric field will be, the region will be, what is there inside the region means field lines will be there. And this electric field lines, how that got, how they think the idea of writing electric field lines by looking at magnet. Even in magnets, no, magnetic field will be there. Field lines will be there, magnetic field lines. You can see these magnetic field lines when you take a bar magnet, and if you put near the nails of iron nails, what happens? The way the iron nails attracted towards the bar magnet, right? It will show the how the magnetic field lines. In the same way, electric field lines it will be written. Okay. And one more thing is, this electric field lines properties, you see, they are always, you know, parallel. Okay, and if I take the electric field lines for both when two charges are combined, for example, positive and negative charge. Okay, from positive charge, electric field lines will originate and it will terminate towards negative charge. You see, okay, because positive charge always a source of electric field line, negative charge is end point of electric field line. Like this, it will be like. Okay, okay. If I take same like charges, what will happen? This there is no like, because of repulsion, electric field lines never move towards the positive charge. Here also it will give electric field lines. Here also it will give electric field lines. So both are originators of the electric field lines. That's why they will start repelling. Electric field lines will start repel. See? Okay. There is no, see, these electric fields from this charge to this charge, there is no moving, because both are same charges, right? So both are starting originators of electric field lines. There is no termination. Okay, so but here it is same charge, you see, it is starting from one charge, and you see electric field lines from positive charge going and ending at negative charge. It is not again starting from negative charge and coming to positive charge. It's not happening. So this is not making a complete loop. It's making a half loop. Understood? Only half loop will be there. That's why the property of electric field lines are, they will never make loop. Okay, they will never form a loop. They will never form a loop. A loop. Loops will not be there. Correct, right? Okay, there is no complete loop. There it's maybe half loop. Okay, so complete loop will not form, because they will originate from positive charge and they will terminate negative charge. So, but if in case of magnets, it will be there, because in magnets, what happens? The positive north pole of the magnet is a source of magnetic field lines, and south pole is the outside the magnet. What happens? Magnetic field lines will move from north pole and end at south pole, right? But inside the magnetic field lines start from south pole and end at north pole. That's why you see it is making complete loop. Okay, so magnetic field lines forms a closed loops, but electric field lines will never form a closed loops. Okay, closed loops. And magnetic, if you want to know what is the direction of electric field at any point, you just want to draw the tangent. Okay, the tangent at any point on the electric field line gives the direction of electric field. Okay, the tangent, if you draw on the electric field, the tangent on electric field will give the direction. Okay, will give direction of electric field. This is about electric field lines. So electric field is very important. Why I am discussing electric field? Because Gauss law it's an advanced way of teaching this electric field. Okay, that we will discuss now. So more the electric field lines means more the charge. Strength of the electric field lines is more, means the electric charge will be more. That means more charge, more number of field lines will come. That means that area is having more electric field strength. Okay, so this is the properties of electric field lines. Now you please, now you'll come. Why this Gauss law is there? See, Gauss law. Actually, Gauss law is the advanced way of explaining about electrostatics. Electrostatics means what? Whenever a charge is at rest, you can find the force of for a charge, whether force of attraction or repulsion for the charge. Correct, right? So Coulomb's law will be a limit because it will only explains for the charges which are at rest. Yeah. Anyway, we are discussing only about electrostatics, right? So Q1 and Q2. Two charges should be there to explain Coulomb's law. Coulomb's law is applicable only for the charges where there are two charges. That too, it will explain about force. Now, this wave, there is only one charge, so we cannot give Coulomb's law. We cannot use Coulomb's law. So that's why Gauss law is more advanced. It's a more advanced tool or law to explain anything, to explain electrostatics. It's a more advanced. You'll understand. It's very, very important. You'll understand. So Coulomb's law is the basic. Understood? And this Gauss law will also give the concept of electric flux. Okay? So what is electric flux? You see, electric flux. You see, what is electric flux? You see, whenever electric field lines, I said no, from the electric field means there is electric field means there is an electric field lines. Electric field lines are the representation of electric field, right? These electric field lines from any charge or from any source, if they are moving, okay, the representation of electric field lines, I will write it as E vector. If electric field lines are there means electric field is there. Understood? When these electric field lines are passing through any surface area, any one surface area when they are passing, this is surface area of cross section E. Okay, when these electric field lines are passing, this is what we call flux. Okay, flux we call. What is flux? The number of field lines passing through a given surface area is what we call flux. Understood? So flux is represented by the letter pi, okay, which is flux. Number of field lines per given area. Number of field lines, number of electric field lines, that too, not magnetic field line, that is also there, magnetic flux. So number of field lines passing through a given area, passing through a given area is called electric flux. Electric flux. Number of field lines, electric field lines, okay? Number of electric field lines passing through a given area is called electric flux. So you can write electric flux pi E is equals to electric field lines into area. Electric field lines is a vector and area is a vector. Vector into vector if it is giving a scalar, because flux is a scalar. Okay, electric field lines passing through a given surface area is a scalar. So that's why you will write a dot product. Okay, the product of two vectors is a scalar, then you should apply dot product. Multiplication of vectors is very tough. You need to apply the two forces, which is dot product or cross product. Okay, so when you will apply dot product, when two vectors are giving a scalar, when you apply a cross product, when two vectors is giving a vector. Understood? So I will just give some topic about it. So pi is equals to, for example, if a vector dot b vector is c vector c, that means c is a scalar, because dot product we are using, which is ab cos theta will come. It's a scalar. If you take a vector and b vector, after multiplication you are getting c vector, c is a vector, then you will get cross product we should use. And a vector, the cross b vector is ab sin theta n cap. It's a vector now, that's why. Understood? So this is about, here the multiplication of vectors. You already studied, right? So multiplication of vectors means when you multiply two vectors, and if you get a scalar, then you need to use dot product. If you get a vector, you need to use the cross product. Okay, so that's why it's a additional information. Maybe you people know this. Okay. Now this is E vector dot E vector, which is EA cos theta. Okay, electric field is a vector, right? It has a direction. Now area is a vector, correct, right? Area is also a vector. If this surface is there, this surface is having, this surface means it's a surface area. It is having a direction which is always normal, like this. Understood? 90 degree for the surface, which is perpendicular to the surface area. That is the direction of area. Understood? Now here the direction of area is, this is some area, right? Okay, this is some plane. Plane is having a direction which is n cap in this direction. Okay, and even electric field lines also in the same direction. Then theta will be 0. Theta is 0. If for example, if this plane has some different direction like this, and if the electric field is this, then there is an angle between these two, that is theta. Then that time it will be different angle. So you can use that cos of that angle. So if both are in same direction, then you will get flux which is maximum. Electric flux is E into A, which is maximum electric flux. When you will get maximum electric flux when theta is 0, that means electric field lines direction and the direction of the area vector, that is normal, is in the same direction. That is what we call maximum flux. Okay, when angle between E and A is 0, in the sense if electric field direction or electric field lines direction is parallel to area vector or direction of area vector, okay, then theta is 0, then you will get flux is maximum. But if the theta is 90 degree, in the sense if electric field line direction is perpendicular to the direction of area vector, then you will get flux is 0 or minimum. Okay, electric flux is minimum. So what is flux? Flux means electric field into area. Understood? So this is the basic concepts you should know to learn about Gauss law. Please take. Yeah. Now what is Gauss law? We'll see. So Gauss law. What Gauss law says? Gauss law says that the total outward electric flux which is equals to 1 by epsilon naught times the total charge present in the surface of that closed surface. It's a closed surface. What it means? The total outward electric flux from any closed surface, the total outward electric flux from any closed surface is equal to 1 by epsilon naught times the total charge present on that surface. Total charge present on that surface. See, here the total outward flux, electric flux from any closed surface. They mentioned it is a closed surface. He mentioned Gauss. Okay, so any surface you take, it should be a closed surface. Okay, then the total flux depends on the charge. Okay, so this is what Gauss law. Now Gauss law has some it's a Gauss law you can apply for any surfaces that should be closed surfaces. Understood? Even if it has an open surface, for example, we will use Gaussian surface. So what is that Gaussian surface? You just see, whenever actually Gauss law can apply for any shape, but we should use Gaussian surfaces. So there are different ways of charge distribution. Number one, okay, and there should be symmetry. What are the symmetry of charge distribution? You just see, yeah, 1 minute. For example, I have a spherical surface body, a sphere. If there is a charge on the sphere, on the surface of the sphere or anywhere, because always charges will just accumulate on the surface of the sphere. Understood? So if there is a charge on the sphere, what will happen? The electric field lines from the sphere will come out in every space, because in every area, all throughout the sphere, okay, equally the electric field lines come out. And the total, this number of field lines which are coming out from that spherical body is what we call flux. All the field lines will come out from that spherical surface. Okay, so this number of field lines which are coming out from the spherical body is 1 by epsilon naught times the total charge which is present, which is Q. If the charge is just Q. If the charge is anything, maximum means you should, that is a, you need to write. So this is the total flux which is coming out. That means number of field lines through a unit area, it depends on the charge present on the surface. Okay, and what about this epsilon naught? Epsilon naught is the permittivity of the free space, because it is the field lines are coming to free space, right? They are coming out of that spherical body. So that's why this is the permittivity of the free space. Permittivity of free space. How much its value is? 8.854 into 10 to the power minus 12 farad per meter. Okay, that means what is permittivity? It is the ability of the medium to allow the field lines to pass through it. Okay, the ability of the medium to allow the field lines to come out from that medium is what we call permittivity. Okay, so this is what we call the Gauss law in any closed surface. Now that surface is closed surface. If it is not closed surface, if it is open surface, what to do? For example, I will take one surface, hemisphere. I will take half of the sphere. Okay, this is a hemisphere. Now I will place a charge on, no, it is not on the surface, it's somehow little bit height, some height is there. Charge is here, surface is hemisphere. It's not complete sphere, it's not closed, and charge is not on the surface. Now, how Gauss law you can apply? Okay, so for that Gauss says, please use this the Gaussian surface. Okay, use Gaussian surface. Gaussian surface. What is Gaussian surface? A Gaussian surface is an imaginary surface. It's an imaginary surface. Imaginary. Okay, you just imagine to complete this spherical surface and to make it a full spherical surface. Okay, this is an imaginary surface. Okay, used to apply Gauss law. Used to apply Gauss law, or to use to verify Gauss law. What is the imaginary surface? How we can apply? You see, there is a hemisphere, half sphere, right? Now I will apply Gaussian spherical surface, which is like this. You see, I will just apply a half sphere again, so it will become complete sphere. Okay, if it is not clear, you just see here. Yeah, it is half sphere. I'm sorry. Wait. One minute. So take, yeah, this is hemisphere. Charge is here. Now to make it a complete sphere, just one more half sphere we add. That's what? Complete sphere. Understood? So this one is a Gaussian surface. Which one is a Gaussian surface? This one. Whatever I draw it. Okay. You see? Yeah. See, here hemisphere is there. Here charge Q is there. Correct, right? Now I draw a Gaussian sphere. Okay, this is spherical Gaussian surface. I made it complete. So it is full. Now it is closed surface, right? Now you can apply, if it is a closed surface, apply Gauss law, which is total outward flux is equals to electric flux is 1 by epsilon naught times the total charge, which is Q here. But because of the charge, the field lines are passes through like this, right? Yes, field lines will go like this. But there is no possibility that field lines will go up because surface is not there. We just draw a imaginary surface just to apply Gauss law. So only field lines passes through the half surface. That's why it is 1 by 2 into Q by epsilon naught is the answer. This is the total outward electric flux through a hemisphere. Okay, so such type, so many examples I'll give. So just listen. Yeah. Now you see, before I was drawing, there was a hemisphere and charge is kept here. This Q, what I did, I draw a Gaussian surface. So to complete the surface. Okay, now what happens? The electric field lines passes through a closed spherical surface. This is a closed. I draw a Gaussian surface. Correct, right? Correct, right? I draw a Gaussian surface. It's closed. Now the field lines will just come out and the total electric flux is, okay, this Q divided by epsilon naught, but he only half of the surface is there, that's why 1 by 2. Correct, right? Now you take one more example. There is a cube. There is a cube. Okay, and if the charge is there at the center of the cube. Okay, now whenever charge is there at the center of the cube, what happens? The electric field lines will come throughout the surface of all the 6 surfaces of the cube, right? All the 6 surfaces of the cube, electric field lines will come. So what is the total electric flux according to Gauss law? The the total electric flux is Q divided by epsilon naught, since it is a closed surface. Now, if I ask what is the electric flux from any one surface, for example this surface, what is the total electric field lines coming out is, it is 1 by 6 times Q by epsilon naught. Correct, right? Because only one surface I am taking. Here all electric field lines uniformly they will come out from all 6 surfaces. But if I ask what is electric field line in only one surface out of 6 surfaces, it is 1 by 6 Q by epsilon naught. This is what how to apply Gaussian's law. So here it is closed surface, it is given. Here it is open surface given, right? So we closed it by using Gaussian surface. Now what are the 3 types? How we can apply Gaussian surface? Here there should be a symmetry in the, while taking the Gaussian surface, we should take symmetrical charge distribution. Symmetrical charge distribution should be there. Charge distribution. What will be there? Symmetrical charge distribution. Number one is point of symmetry. Point of symmetry. Number 2, line of symmetry. Line of symmetry. Number 3, plane of symmetry. Plane of symmetry. See, what is this symmetrical charge distribution? Point of symmetry. You see, this point of symmetry I will explain here. I'm sorry. Yeah. This point of symmetry, you see, you can explain easily. If I have a spherical body, charge is there at the center or on the surface. Now what happened? The charge from each point on the spherical surface, this is a spherical surface, the surface, okay, you take any point on the surface, it is at equal distance from the center or from the charge. Correct, right? It is R you take, or you take capital R, anything is there, okay, capital R you take. It is at equal distance. No, big. Now if you take a spherical body, center you take one charge, okay, each point on the surface of the spherical body is at equal distance, correct, right? Equal distance, you see, R, equal distance. That's what we call spherical symmetry, okay. It is spherical symmetry. That's why number of field lines are also, it is in symmetry. I mean, the number of field lines also passing is equal. If for example electric field lines will pass through the spherical surface, okay, you see, at any point, if the point is somewhere here, point P, okay, or somewhere on the surface, a point may be anywhere on the spherical surface, the electric field lines will be moving is same, correct, right, at same time, okay, there is no change. This is what we call spherical symmetry. Spherical symmetry. So if you take, I was taking in a half spherical body, right, half spherical body, and if charge is there Q here, why I am drawing the complete sphere using Gaussian surface? Because it follows spherical symmetry, okay, that is what we call point of symmetry. A point of symmetry means it is spherical symmetry. Spherical symmetry. Spherical symmetry will be there. Why spherical symmetry? You see, you take any point on the spherical body, any point, okay. Now the electric field lines are moving through the point is equal compared to any other point on the surface, okay. So the number of field lines passing is the same. That's what we call spherical symmetry. It's a point of symmetry. Each point is exactly equal distance. That's why we draw this Gaussian surface. Understood? We draw the Gaussian surface as for the point of symmetry, which is spherical Gaussian surface. This is spherical symmetry. We will draw the Gaussian surface, which is spherical Gaussian surface. Okay, we'll write here spherical Gaussian surface. Spherical Gaussian surface. Spherical Gaussian surface. Okay. Now, line of symmetry. This one is also easy. You see, line of symmetry is very interesting. Just listen. For example, we have an infinite wire, and this wire is having all charges. Okay, one positive charge wire. You can see, right? It's not possible to see. Yeah, I will draw a infinite wire having the positive charges everywhere. Okay, this positive charge, you take any one point near the wire. Okay, the distance from the charge to the point P is, I'll take R. Okay, now you see, surrounding the charge, this charge is the source of electric field. This is the point P. Now electric field lines will move through this point P. You take anywhere, the electric field lines are equally flow throughout the charge. Correct, right? You take the point this side, this side. What happened to TV? Sometimes this will not work. Okay. Yeah. 1 minute, 1 minute, 1 minute, 1 minute, 1 minute. Yeah. You see, if this is point P, the distance of the point P from the charge at this side, if the point P is this side, it may be anywhere. Okay. This side, this side, this side. It is equal distance I will take. Now, the electric field lines also will move equally. It will make like a circle. Correct, right? So, electric field lines are all move in all directions. All directions it will move. Correct, right? Even this positive charge is there. Electric field lines will move in equal direction in all ways. Correct, no? Entire throughout the point is actually equal distance. Here you take the point P, which is at a distance R. This side, like it will make another circle. Like each and every charge will distribute the electric field lines equally throughout its surface. I mean, throughout its, surrounding the charge. So every charge, if you take, it will make a cylinder. That's why a line of symmetry is a cylindrical Gaussian surface. Cylindrical Gaussian surface. Cylindrical Gaussian surface. Okay. Okay. So what is the cylindrical Gaussian surface? Once again I will explain. Listen here. So if there is a charge, of line of charges in a wire. Now what happens? This charge is having, for example, I will take one point P here. Okay, the distance is R. This point P throughout the charge in 360 degree, it will be at the same distance R. Correct, right? Now electric field lines also move equally. Okay, so that's what it will make a cylinder. Every charge, you take the point here. From the center, this electric field lines will from this charge also electric field lines will come. From this charge also electric field lines will come. That is also one way of explanation. But what I am telling is, each and every charge will give electric field lines in all directions. Like that, each and every charge will give electric field lines. If I take all that, it will create a cylinder. That's why it is cylindrical Gaussian surface. Understood? So at each and every point on the cylinder, that too the curved surface of the cylinder, not the plane surface of the cylinder, curved surface will give the electric field lines. That's why the line of symmetry, see, all positive charges in a line, which Gaussian surface we will choose? Cylindrical Gaussian surface. Understood? Now the plane of symmetry, this is the third symmetry of charges. Okay, so this is the third one. You just see how I will write. Plane of symmetry. You take infinite plane of charges, infinite sheet of charges. This is a sheet. The charges are there, positive, positive, positive. There is infinite sheet. Okay, all charges are on the surface. Now, how you can find the total flux which is coming out any point P? This is one point P. How the total electric field lines or flux which is coming at this point P due to this infinite plane of charges. Okay. Now, what we need to do? Okay, from this charge electric field lines will come, from this charge electric field lines, from this charge electric field lines. So, all these electric field lines will just come towards this point P. All these electric field lines will come towards this point P. Okay, so how we can measure this electric field or electric flux? For that, Gauss says, please use the pillbox. Okay, if I use, for example, any of the spherical surface, for example, I will use this point P is here, no? Okay, I will draw a spherical body. 1 minute, here it's got taken. For example, I have a plane, infinite plane, okay, where charges are there everywhere. Okay, now this is the point P. What is the total electric field or flux passing through that point? We need to find. Now, for example, if I want to find, okay, the maximum charges, they will give electric field lines through that point, correct, right? Now, how much flux it will move? So, what you need to do, you just draw a pillbox. That pillbox should be covering with the point. This is the pillbox or a cylinder, some type of cylinder which is passing through the sheet. Understood? So, this is the pillbox where Gaussian surface we draw as pillbox. This is the pillbox as a Gaussian surface, and because of the charges, the electric field lines passes like this. You see? See? Through that point. One phase, another phase, back space will be there, no? Because it is a sheet. Front sheet, from front sheet, these field lines will pass. From back sheet, these field lines will pass this side. So that's why Gaussian surface we will use for the plane of symmetry is pillbox. Pillbox. Okay. So this is a symmetrical charge distribution. Here, is it possible to apply, spherical Gaussian surface? If we apply spherical Gaussian surface, what will happen? It's not possible. You can't find the number of field lines. The symmetrical value will not come. The symmetry will not come. If you want, you will try. What happens? For example, I will take the infinite sheet. Infinite sheet I will take. Okay, charges are there. Now I apply a spherical Gaussian surface, for example. This is the point P. If I apply spherical Gaussian surface, it's not possible. This charge is electric field lines will give from here. This electric field lines will give from here. Okay, it will give from here. This charge will give electric field lines from here. So what will happen? This side, the point P is this side. Correct, right? Now what happens? The charges are actually not placed. Each and every charge will have a different distance from the point P. Okay, so it's not possible to give the symmetrical electric field line. The charges are not symmetrically placed in spherical Gaussian surface. That's why we will not use spherical Gaussian surface. We will use only pillbox or a cylinder which is inserted inside the sheet. So this is the way of calculating total flux which is coming out. One example also you can do a point of symmetry which is spherical Gaussian surface. I will just take it. Yeah. If for example you take a a charge is there. Charge is there. See, the importance of Gaussian law, Gauss law, Gaussian surfaces or Gauss law is how many charges will be there. We can find total electric flux and electric field, but you can't find using Coulomb's law. Coulomb's law will give just force between the charges. even it is one charge or multiple charges. But Gauss law will give the so much information. What is the importance of electrostatics? Electrostatics we will use to find the field, electric field, right? Okay, and also electric flux. So this Coulomb's law is very, very important. How many number of charges will be there on the surface? We can use Coulomb's Gauss law to find the electric field, but it's not possible by Coulomb's law. That's why Coulomb's law is basics, means Gauss law is advanced way of measuring electric field. For example, if there is a charge, okay, on the spherical Gaussian surface. Now, this charge I place at somewhere at the center, you take, or at any the surface, on the surface, okay. Yeah, charge is there, Q. Now, if I take the radius of the spherical body as R, this is the distance of the spherical body from the center. That means radius of the spherical surface. Okay. Now, if I take a point, this point P, P0 I will take, or P1 you take, or P0, fine. And this on the surface which is P1. Now, what is the total flux which is passing through the P0 point because of the charge? The distance of the charge from the center to the point is, I will take it is R, small r. Okay. So, what is the total electric flux? Electric flux or electric field which is coming out through the point P. So, you can tell, if I place a charge on the spherical body, what is the total electric field at that point P0? How we can find? We can find using Gauss law. So, what Gauss law says? Gauss law says, please draw the Gaussian surface. It says that only. Gauss says, please first draw the Gaussian surface. How we can draw the Gaussian surface? Where they are asking to measure the electric field, this point. So, this point, through this point, please draw the Gaussian surface. Since there is a point charge, Q is a point charge, draw the spherical Gaussian surface. I already mentioned, okay, for a point symmetry, spherical Gaussian surface you should take. Here only point charge is there, so please take spherical Gaussian surface. You see, from this point, from this charge to each and every point there is equal distance, correct, right? Each and every point is equal distance from the charge Q. So, it is symmetry. Symmetry is there. That's why it is called spherical symmetry. Now, from the charge Q to any point you take on that point P is, you see, it is at every point you take, it is at equal distance from the charge. That's why it is called spherical symmetry. Okay. Now, the flux passing through this point, through any point in this surface, Gaussian surface is same. That's why it is called spherical symmetry. Okay. I think now I hope you understood. Now, what is Gauss law says? The total outward flux from any closed surface. I closed that surface, right? Because the point P lies on the surface now. It is a closed surface. So, that is the importance of Gaussian surface, imaginary surface. Now, it is the total outward electric flux is 1 by epsilon naught times the total charge inside or on the surface. Okay. Okay. Actually, charge will lies on the surface. Now, this is equation number 1. Now, what is another equation? The total electric flux is electric field into area, right? E vector dot A vector. Now, it is electric field is in the same direction. Now, you see, at this point electric field will come, electric field lines will come in the same direction, and the surface area vector also in the same direction. Area vector you can write n cap, normal vector, because the area is there, means this is the area. Okay, at that point some area will be there, no? This area, its direction is in the same way, I already explained. So, now both are in the same direction, means theta is equals to 0, then it is E into A. Okay, this is equation number 2, because cos 0 is 1, cos 0 is 1. Okay, sorry. Sorry, 1 minute. Yeah. Anyway, I will just yeah. So cos 0 is 1. Now what is the total electric flux? This is equation number 2. Now compare equation 1 and 2. Flux same. So E into A is equals to 1 by epsilon naught times the total charge. Okay. Now you can write E is equals to 1 by epsilon naught times the charge divided by A. So you can find electric field coming through the spherical surface at that point P. You can write E is equals to 1 by, what is the surface area of a spherical body, which is 4 pi r square into epsilon naught q by epsilon naught. So you can write electric field E is equals to 1 by 4 pi epsilon naught, okay, q divided by r. Oh, sorry, 4 pi r square, right? It's r square into r cap, direction r cap. That is the electric field at the point P. At the point P. Understood? Okay. Now, if you take electric field on the surface, this is one. If you take electric field on the surface, for example, you take this case 1. If it is case 2, what is case 2? If electric field, if you want to find on the surface at point P, which is at a distance r, radius of the spherical surface, right? R, P1, okay? You can write P1 at P1. Now, what is small r will be capital R, correct, right? Now, what is the new electric field? E vector will be equals to 1 by 4 pi epsilon naught q divided by r square into r cap. This is the electric field on the surface of the spherical sphere without Gaussian surface. You see, the point P lies on the surface, but here it is P naught is lying on the outside of the spherical body, and that's why I use the Gaussian surface, imaginary surface. If it is not there, if it is on the surface, directly you can write, okay, small r will be equal to capital R. So this is a Gaussian surface, Gauss law we applied for a spherical body. Understood? Okay. So if the point lies inside the spherical surface, what is the answer? For example, here P2 I will write, here P1 and P2. And the distance you take r dash, if it is inside, the electric field lines are same, correct, right? The number of field lines passing through the Gaussian surface is same, only as the distance changes, because that's the electric field at the P2 is same, because charges will actually not accumulate on inside the spherical body. It will just come out from the spherical body. On the surface it will accumulate maximum. So since the charges will accumulate on the surface of the spherical body, then the electric field lines are same. Correct, right? So it will come the same. Now if you want to draw the graph of electric flux or electric field with respect to the Gaussian spherical surface, then you can write, see here. Now I got electric field outside the spherical surface is 1 by 4 pi epsilon naught q divided by r square into r cap. It is on the surface 1 by 4 pi epsilon naught q divided by r square into r cap. Okay. Now you can just draw the graph. Draw the graph. So here, yeah, just inside it will become, I just mentioned, if the point P is inside, okay, so that electric field lines will originate from the surface, right? There is no surface here. So here, so electric field inside is especially 0. Okay, just you note this. So inside it is 0. Guess flux will not come out from the surface. I missed that point. Here you see, if the point P is inside the spherical surface, what will happen? There is no flux only. So there is no flux means what is electric field? Electric field will not be there, because point P lies inside. The field lines will just go this. Here it is surface. Here there is no surface area. So this flux concept will not come. It is E into A. Electric field lines, how much are there inside, you can explain. So that's why it is 0, because the area is 0. So that's why inside electric field is 0. Now, if I take the graph of R with respect to electric field E, how that will come? How electric field will come? Just see. 1 minute, I'll draw little bigger. So the graph, this is R, this is electric field E. Okay. Now you see, I say this R will be equal to capital R till the radius of the spherical body. This one. Okay, that is on the surface. Now this remaining is outside. Remaining is outside. Now electric field. Electric field E maximum will come, maximum electric field will come on the surface, correct, right? Now totally outside it will goes on decreases like this, because it is 1 by R square, right? It goes on decreases. Inside the electric field line is 0. So this is the graph, understood? So here it will not come like this, little bit it will, the graph will be sweep. Not sweep, what we can see, exponentially it decreases. Exponentially decreases. Okay, so this is when R increases greater than R. When R equal to R, it is maximum electric field. Inside the spherical surface, the electric field is 0. So this is the Gauss law used for the spherical surface. Okay. So in the next, I will also discuss about Gauss law in cylindrical surface for infinite wire and also the plane sheet. I will discuss. Then we will move the importance of significance of Gauss law. So this much is enough today, and I will start the new lecture next class. So take care. Bye bye. Thank you.